Hey, hi everyone. Welcome to Research Jam Session 2, where we'll be discussing transformers without normalization. I'm Ayush, CEO of Genloop, and I'm joined by various members of Genloop and outside, um, looking to discuss this paper. In Research Jam, we try to pick one of the top papers according to our uh, research workflow uh, and discuss what was proposed, what could be different, and actually just brainstorm on this entire paper. Next slide, please, Vansh. So, just a quick idea about Genloop. We are in the space of building domain intelligence seamlessly. And we do that in three simple steps. One, we integrate with your enterprise data. We make the entire dev cycle autonomous. So, from observing to creating training data, to training models, monitoring them, and the biggest piece, continuous learning. So, the model actually learns from the errors it is making. And this is something that you can directly integrate with your application. Once can we do it on full screen? Perfect. Yeah. And the papers that we have chosen today is from our LLM Research Hub, where we bring the top curated papers by ranking them based on popularity, impact, and relevance. And next slide. So this is a selective space to discuss Gen AI research periodically. We'll have this bi-weekly and would love to have more of you attend. It's an exclusive space, so we are very selective in letting people in, but that is what ensures the quality of the discussion that you're wanting to have. Now, over to Vansh and Ayush. They are the speakers for today. They're both from Vision and Language Group IIT Roorkee, and they're interning with Genloop. Looking forward to the moderation by you guys and looking forward to discussing this paper.
Hi everyone. Today the paper that we'll be discussing is Transformers Without Normalization. This came out recently and it was released by Meta. So generally, when we look into the sort of changes that normalization layers, that people play around with normalization layers, it's generally by changing the way you calculate the statistics in that, right? But in this paper, what they challenge is that they replace that normalization altogether and replace it with a simple function, which they call dynamic tannage, which there's presented here, tanh alpha X, right? So we'll go more into that, like how it was implemented in the later slides. So the key takeaways in this paper were that they analyzed the normalization layers, input and output relations, and figure out what exactly their purpose is and how it's transforming the input. So in the initial layers, they found that it's mostly linear, but in the later layers, they saw that there is a S-shaped curve and a non-linearity that this normalization layers are bringing in. So, given that there is a similarity between the shape of these normalization layers and the scale tanh function, they propose a new function called dynamic tanh as a replacement for these normalization layers altogether. So, and they find that under various settings, these models match or exceed the performance of their normalized counterparts. So, so before we begin, what exactly DYT is, let us talk about what exactly normalization layers are, right? So in the modern transformer architectures, we mainly see that there are two types of normalization: layer normalization and root mean square normalization. And these two differ mainly in the way you calculate your statistics. So in layer norm, you do it for a token, and in RMS norm, you remove the mean, you take the mean as zero, and you just scale it with the root mean square of the tokens. So there is, as you can see, there's the formula. So there, the E is a small constant, and alpha and beta are learnable vectors, and they are called the scaling and the shifting affine parameters, right? And the mu and the sigma square denote the mean and the variance of this input. So any questions like as to how normalization layers work? All right. So taking no questions. Also, they also deal with batch normalization, but we'll cover that later because there were certain issues with that. So,
Just once maybe we can discuss why at all we need normalization. So for
sure.
some
Yes.
people who not coming from the traditional ML background, that could be a good discussion, to educate or to just explain the requirement for normalization at all.
So the main thing with normalization is that it helps with better stabilized and quicker convergence during backprop, right? So with that, you get better efficiency during training, and then there's less chances of divergence. Additionally, they've seen that in general it performs better if you have these normalization layers. So as you can see, most people in neural, whenever they're working with neural networks and transformer architecture, they try to replace the attention layers or some other layers. But la- uh, layer normalization is something that is like consistently fixed, and not a lot of people try to change that. So this is basically what they're trying to challenge here. So now moving on to that. Uh, also, layer normalization is something that is used in most transformer architectures except LLMs. So LLMs use RMS norm. So first we'll discuss the input-output relations in layer norm. In VITs, wait,
Let me just add a couple more points to the normalization aspect, and then of course if anyone also wants to add to it. So definitely the benefit of normalization has been studied empirically and theoretically both. Empirically, I think it people saw that it was indispensable to training, and without it,
hmm,
the models were not training well, as in the
hmm,
losses were not achieving their global minima or the best local minima that could be achieved, and the weights were actually diverging. So basically, either
hmm,
because of exploding gradients or vanishing gradients, like the training could not converge. What
yeah, yeah,
normalization essentially is doing is, so in this entire LLM, it's like matrix multiplication, then added with few things, and another matrix multiplication, etc. Now, this X that you're giving as an input could be multiple values. Like you
hmm,
could be starting from a 10, 100, from a 0, zero point 0.1, 0.2, etc. And for the model to take all these X values and be still able to infer something meaningful, like from the input perspective, we need something that could be in a range, and which is understandable to the model in relative terms. So if I'm taking basically if my X is something as an input from 100 to 1000, and similarly for another use case, my X is in the range of 0 to 100, um, how might I make sense of that in a given range so that my ML model still works? So traditionally, normalization has been, just minus by the mean, divide by the
hmm,
variance, and then do some learnable parameters for gamma and beta. Learnable parameter just helps to make sure that the RMS is also optimized, or the normalization is also optimized. Um, so that is where we see even the back propagation of gradients, basically backward propagation of gradients also working when we have been able to do that normalization to propagate it back. So that was just
yeah,
couple points I wanted to add.
yeah,
Are you
yeah.
sure to say normalization as similar to standardization in this scenario? Okay.
Like, right, yeah. So
Huh.
it's very that's a similar intuition. Like standardization of inputs is one of the benefits that normalization is giving. Of course, there is the other benefit of making sure that the back propagation of gradients is not vanishing or exploding.
Okay.
Yeah, so pretty much you can summarize it like they try to squash the values into a smaller range rather than the extreme huge range that they have, which is kind of, you can say, an intuition behind using TANH as well in the later stage. So I then we can move on to exactly understanding how the input output relations work. So first they try it out on a VIT vision transformer, wave to wake model, which is for audio to processing. And then you have DIT models, which is the new diffusion transformer models, right? So here their main observation was that in the initial layers, as you can see in layer 5 here, you can see that it's primarily linear, which is what they were expecting. Because when if you look at normalization, it's just two linear transformations, one subtraction and then one division. But as they go on to deeper layers, like layer 15, 20, 25, you can see that there's this sort of an S shape, right? And this S shape resembles the tanh function that is present. That the other tanh function, which was their main motivation to propose this as a replacement. And the primary reason why they feel like this S shape comes is because, as you can see, that layer normalization works in a per token manner, right? So only linearly transforming each token's activation. But if we take this collectively, we'll see that it's not really a linear function. It is that as tokens have different mean and standard deviation values, the linearity does not hold collectively on all the activation functions. And this is like their main hypothesis as to why there's this non-linearity being introduced. And then, so then moving on to exactly the Spanish function. So given that there is this S-shaped function, but it is varying according to the layers, and there is a difference in terms of the ranges and in terms of the slopes that exist, they add an alpha here, which helps to scale. It is a learnable scalar parameter, which helps to scale the input. And just to be clear, it's like this is how it's different from normalization is that it operates on each input tensor, each input element independently, and there is no sort of aggregation or statistics being calculated at all. And so this, as you can see here, the learnable affine parameter scaling and shifting, they have retained that in their DYT function as well. So they're mainly replacing the standardization here. Any doubts till now as to how this DYT function works?
No, I don't think so. Once can you go back to that slide of the formula? The next one.
Yeah.
This one, yeah. Mm, mm. So definitely, like since we're not required to do statistics over all the inputs, this saves compute and flops as well.
Exactly. So their main achievement is that they have achieved like the same performance with a little and even increase in the performance in some cases with much faster efficiency, much better
Mm,
efficiency.
makes sense. Makes sense.
And
Yeah, you
yeah,
can.
and also another intuition behind using tanh is simply when you think of normalization, as I said before, it's squashing the values into a better range, right? That's
Correct.
exactly what the tanh does. It's
Yeah, of
squashing the
course.
value. So that just makes more sense.
Right.
So now I guess we can move on to the initialization of the learnable parameter
Hmm.
alpha.
Hmm.
So as they found that in non-LLM tasks, the variation of alpha did not really matter at all. So it's almost similar. They're getting similar results all throughout, except in one case, which was in VITL. And they found that after a value of 0.6, the model starts to diverge. And also, they tested it across various learning rates and model sizes, as you can see from this bottom diagram. So the blue ones are the completed ones, and the yellow ones are the failed ones, right? So with the ink, so yeah, just give me 1 second. Yeah. So uh, non-LLM models are relatively insensitive to alpha naught, and smaller alpha naught in general results in better stable training. So these are two key insights for general uh, alpha. And then when they test it across various model sizes, uh, they find that on increasing the model size, it's preferable to have a smaller alpha. And yeah, and lower learning rate. So that's any doubts right now?
Makes sense. Mm. Pretty intuitive.
Hmm. And then we look into the initialization of alpha in LLMs. So the main difference is that they find that it is better to have like fine a little bit fine tune these initial parameters, right? So as you can see, higher alpha naught values for attention blocks improve performance. So they decide to have alpha naught values different for the other layers, like
Oh,
the feed forward layers and such. And then alpha naught values, which are specific to the attention layers, they have a different value for that. And then larger models requires smaller alpha naught values and model which primarily determines alpha naught selection. As we can see from this below table, that they've got various width and depth sizes and then the variation of alpha. So this one's attention and then this one's other.
1 second. Okay, so they're seeing that attention models require higher alpha now. And how
Attention
did
block,
they,
yeah.
yeah, attention blocks, sorry. So how did they actually arrive at these values?
I think these just came simply from experimentation. So there's no really uh, reason behind why exactly they've done this, at least as in the paper, I could not find such reason, but this is purely from experimentation.
Do they also suggest why they require higher alpha not for attention blocks?
Uh, as far as I remember, and as far as I can see from the paper right now, there's no specific reason for this. This is just experimental data.
I can possibly try to give some intuition around it. I may be incorrect though, but
Mm-hmm.
let's look at what higher alpha value is doing. So, in a sense, higher alpha value will make your tangent graph more steep, right? Uh,
Hmm, hmm,
so, um, essentially, it is uh, kind of narrowing the activations in a smaller range, so to say.
hmm,
And that for attention blocks might actually make sense because uh, so if we look at how attention is computed, it's dot product, right?
hmm,
So and the dimensionality of these models is generally very large. So what generally would tend to happen is that uh, a curse of dimensionality will start coming into pictures. So for example, if there are 8192 dimensions and I'm taking a dot product, then essentially if each multiplication has a value of 0.0001 also, the dot product will sum up to 1. So what higher alpha value in a sense is doing is kind of reducing the search space possibly by uh, narrowing down the range of activation functions, and thereby it's possibly helping out attention blocks significantly. And that is what my intuition says, in a sense, if that makes sense.
Mm.
yeah, I think.
So we are saying could it also be the fact that for attention, we actually need to focus on much less tokens than for non-attention blocks? So when we are making the uh, normalization steeper, it works for attention because only few values or basically actually no. Um, we want no that intuition wouldn't stand because higher the value, the final normalized value, the better it is for the attention block. So let's say
Mhm.
the once can you go back to that formula? That was alpha tan h alpha x plus beta, right? Gamma.
Mhm.
Now, what I want um, for my attention block. Now, where exactly is normalization happening after the attention block? That is happening just before we do the dot. No, it's not happening in the QKVs, right? It's happening
No, 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 no.
before
It's not
it
happening
gets
in the
It's
into the.
queue.
happening before.
Yeah, it's
It's
happening
happening
before it
before
gets
the
to.
dot product.
Correct. And it happens after the entire attention is applied.
Yes. For the subs, primarily what I think it was the Llama paper only that shows that applying normalization before the attention block was more helpful, and that kind of makes sense, right? Because again, if you think of it, normalization essentially is giving you a bell curve, right?
Right.
So if my bell curve is spread quite a bit, it means that my activation values are spread in a larger region, which makes my search space very large. And thereby, it will make it difficult for the model to specifically pinpoint the attention regions. So think of a normalization curve where where very few activation values have large, very few of the dimensions have large activation values, and the remainders have smaller ones. Right? In that
No, but
case, the
in this case, isn't like applying this normalization just before attention. Aren't we spreading the inputs more towards the extremes? So let's say uh, alpha is high, alpha is 1 and 0.1. So A is when alpha is 0.1, B is when alpha is 1. When alpha is 1, when they're proposing to have higher alphas for attention blocks, what they're essentially doing is spreading the inputs more towards the fringes. So for the same input, either it will achieve a -1 or 1 faster than, or basically more values of x will achieve a value of 1 and -1 compared to when it was 0.1. It will be more in the narrow ranges, but here it will go to the fringes,
yes.
right? So they're
Uh,
basically reducing the bell curve in some sense, not increasing it, they're reducing the bell curve. And when they're doing it, probably what they want to do is, or basically when they are pushing things more to the extreme, what they want to do is to probably expand the attention of many of the inputs, basically expand the scope of attention. So maybe for longer context, or basically helping the model attend to more tokens than it would be when alpha is low. I might be wrong in the intuition, but that is what I'm carrying from the understanding.
I again, and I can be wrong here, but my feeling is that that's a bit counterintuitive. Again, why I'm saying this is because uh, we can try to answer the question why uh, it was proposed to use multiple heads in the attention block in the first place, right?
Mhm.
Essentially the goal was to divide the dimension part of the attention block, thereby. So what it did essentially was it reduced the search space across those key, thereby making the dot product a lot more efficient because the curse of dimensionality aspect was reduced to some extent.
Mhm.
So when I'm making the value of alpha high in this tanh function, I'm in a sense making the bell curve go more like this. So
Mhm.
uh, most of the logit values will come down to zero, and few of the logits will get a very high value. So in a sense, it's making the work of computing the dot product a lot more efficient by reducing the search space. Am I making sense?
Mm.
And I also want to bring in another point here, why it is possibly bringing efficiency, and that is probably because of the memory bandwidth being one of the limitation. So in order to compute the statistics, basically all the activation values will have to be brought back into the SRAM from the high bandwidth RAM of the GPU. And then basically the scaling and the shifting will have to be done. But what essentially this function does is it makes that scaling and shifting operation independent of the statistic. So the memory bandwidth issue basically gets resolved by this function,
Mm.
and from
Mm.
there it gets
Mm.
the efficiency.
Okay. Like, just to rephrase, uh, uh, like rephrase again on this one from my understanding, and would love to know if everyone concurs. What alpha, high value of alpha is doing is making the tan h more like a gating function or a step function.
Mm.
Like,
Mm.
we all agree that it makes the curve steeper, or basically, and it resembles more like a step function. So maybe for attention, if it is helping, it means a step function will help uh, strongly filter out relevant and non-relevant features. So basically, it will help for better separation of important, non-important features. So maybe, as Sachin, you were saying, bring the focus on important features more and remove the noise, or basically filter out
That's
the noise
exactly
better. Uh,
That's
so
exactly
act as
what
a
it
better
is doing
filter.
in my view.
Correct.
Yes. And that is possibly why it is leading to slight improvement in the performance also, because s- the normal layer norm function will not be getting other activations to zero. But as the alpha, with the increased alpha, many of those activations which are not possibly required are actually coming down quite fast.
Hmm.
So I think
Right.
those memory
And
bandwidth, yeah,
correct. And a lower alpha is required for otherwise, apart from the attention blocks, because there we want better gradient flows. So we want a
exactly.
smoother
Mm.
curve.
Yes, because larger models will be able to hold more memory, right? More
Mm.
attention spans, and thereby
Right.
smaller alpha values would work for it.
Right. We don't want
And
a
for smaller model,
we want dense values there. We don't want a sparse weight matrix there, probably.
yes, that is
Mm.
what my feeling is.
Makes sense. That makes sense. Cool. And then why width? Why is model width significantly impacting the alpha?
Uh, Again,
Lower
this was something like there was
values
no
of
specific reason in the paper, at least. But most probably,
Hmm.
Yeah, so it's correct, right? So model width only will primarily impact, not the depth. So depth basically means number of layers. That to me is not as important as the dimensionality is the deep part of your model, which is generally 1024 and 8192s and so on. Because again, the same intuition comes over here, right? So with larger as the dimensionality increases, I would want my number of heads of the attention block also to go high. Again, so that the curse of dimensionality aspect does not come into play. So
Hmm.
because of the same intuition, I think it is the width part which is
Hmm.
uh, um, contributing more towards alpha selection.
Hmm.
It
Cool. Makes
intuitively
sense.
makes sense.
Makes
I
sense.
might have another intuition behind it. I don't know if I'm wrong. This is
Go
very
ahead, go ahead.
random. But if we look at layer norm, right? So in layer norm, it goes across the entire width, right? So we are
Yeah,
working with that. So when you have more values, you have more variation. And there's a very high likely chance that the mean is not really that high because there are more values, there's more negatives, there are more positives. And the mean might just be towards zero. Uh, right. So because of that, as you can see, if the width is increasing, there are more values that you're working with. Since you're working with more values, uh, the mean is lower, hence alpha is lower. That might like the scaling.
But the scaling part is
Uh,
handled by alpha, I think. So how could mean contribute to it?
Sorry, I said mean variance. This.
Yes,
Uh,
it could be a thing, right?
So what you're trying to do is draw an analogy between the layer norm and this. So what you're saying is when there
kind
are
of.
wider networks, the mean and variance will probably be low. Like when there are large numbers,
Mhm.
that's what you're assuming.
Kind of.
Because things settle down more towards the peak, or basically things get
Exactly.
smoother when there are more samples. Um, so mean and variance will be low, and what that does is concentrate uh, the numbers around, or basically well define
Yeah.
the bell curve. And when we
Mhm.
are saying for model width high, we need smaller values of alpha.
Hmm. Yeah.
Hmm. What we are saying is also not bring things to the extreme, but keep them
Yeah. A
well
little smoother.
distributed.
Yeah.
Hmm.
Well distributed. That could be one possible intuition.
Sachin, you agree with that?
Yeah, I mean, it does make sense. So, for a large dimension, a smaller alpha value will give a closer approximation
Hmm. Hmm.
for sure. Yes, 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 that makes sense. Uh, Again, but there is a fundamental assumption there. So, we are assuming that that the activation values of these dimensions will be smoothly distributed,
Like
and
that.
that's a
That's one assumption.
reasonable.
That's why I was confused about.
Yeah, and that's
That's
Basically,
why I was
that's
unsure of it.
outliers will have less effect. Basically, by law of large
yes.
numbers, in the
Hmm.
distribution, the outliers will have less effect. So things will be more, or basically well distributed towards their actual distribution, which is normally a bell curve. So
I
in that
I agree.
cases, low alpha also helps things to be more at the bell curve.
Hmm.
That makes sense.
Hmm. Cool. Correct intuition. Makes sense.
Absolutely.
And all right, so the next section will be okay. There's one more slide, bye bye. So as I said, that we will be discussing batch norm as well in classical convolution networks. So this is so they tried ResNet 50 and VGG19, and they trained these with DYT layers and trained it on ImageNet 1K, and then test their classification accuracy, and they
Mhm.
found that there was a drop in performance. And their hypothesis for this is that this is because the batch norm layers is appearing more frequently in these convolution networks as compared to how it happens in transformers. And
I somehow feel that, of course, it's a first kind of a proposal. I still feel this DYT is quite overfitted on the experiment that they tried. I don't know.
might be,
Um,
might be.
like having to say that more normalization was required, so this DYT did not work. Um,
Yeah, I think
hmm.
this hypothesis, even I did not really find that convincing. That just there are more layers, so I personally could not like buy into why that's been
It
the case.
seem to be agreeing that basically what they might be saying then is that DYT is a good approximation for normalization if you're not normalizing too much.
That's what, because their main selling point is efficiency.
It's like,
Also,
oh, yeah.
did they apply over all layers or only the final layers?
So in the experiments that they run, how they work is they simply just pick up that layer norm and replace it with DYT,
All
and
So
layers.
that's
what?
all.
Yes.
All,
There can be one
all
hypothesis like
layer
when
norms.
like initial layers we apply the normal like layer normalization, and for final layers we can apply the DYT. because the experiment show like S-shaped curve is find in the last layer.
Yeah, I think that
Yeah.
that might make sense.
You actually bring a good point. Maybe they picked the wrong function for this. Maybe DYT is not the right function when normalization is happening so much. Like,
Mm-hmm.
because when they empirically studied, they find a sigmoid function for layers, right? Maybe
Mm-hmm.
that is not the best function when a lot of normalization is happening. I don't know.
Do they have any ablation study with different alpha values for this batch norm with DYT?
I
Don't
think
think
that
they
that's covered in the experiment section. With batch
not for the batch
norm, no.
norm.
Not with batch norm. No. Not with batch norm. With batch norm, this was even in the appendix section, like a very small. Like
Did they,
the amount of content that I have on the slide is all they had in the paper.
so did they fix? How did they fix the alpha for this batch norm on ResNet? Like, was it the one they picked in the llama
Mm,
exercise?
they did not mention that at all. It's an
Would it be
appendix
that they did
section, so
not experiment it well enough in this case for the batch norm? I
mu-
don't know.
there might even be a chance that they did like much more extensive experiments and all of them failed like much worse, right? So they could not reported it.
Okay. Another thing. So in batch norm, essentially the normalization is happening for each activation across across the batch dimension, right?
Right.
And the batch dimension generally for Cornet would be at the max, let's say 16, 4
Mm,
or 8 or 16.
mm.
Uh, is it then I mean for such small samples, number of samples across which normalization is happening, um, can this dynamic Tanh function anyways approximate the normalization function, underlying normalization function? I'm not
I
sure.
think
Uh,
I think like the way they showed input output relationships between layer norm, right? If they would have given that for batch norm as well, then it would have been like much better to understand how this was working.
Possibly that's what, like, maybe with batch norm they did not do a proper study on what is the good function. Maybe tangents is not the best function for batch norm kind of a requirement. But anyways, like if you look at the standardization of it, a sigma should work. I just think that it's part of more experiments and tunings and tweakings that need to happen.
Potentially. Yeah.
but then sigmoid will bring in fundamentally the same issue, right? Uh,
Hmm.
I know
because
that's what,
no.
like
Sorry.
possibly
Yeah.
no, either one difference between DYT and batch norm is that with DYT we are losing the information sharing between different batches, or
Hmm.
when we're talking about layer between different layers. Does that help so much with connects when there is certain kind of standardization happening across multiple examples? Is that helping the ResNet network in some ways than when we are just standardizing and squashing the values between -1 to 1?
I think possibly yes, because imagine the kind of variations that exist in images anyways, as compared to linguistic, the uh, one image could be completely black and white, one sample. Another sample could have significantly divergent characteristics in terms of pixel values. So I think probably a batch normalization statistics in case of such high variances becomes important and cannot be approximated by a dynamic time function. Possibly, I mean, one of
Maybe
the
maybe it's
hypotheses.
too harsh on the image data set because
Yes,
it's more diverse, as you said.
yes, that's exactly what my intuition is as well.
Mhm.
Also,
Maybe
did
that
mention
go ahead.
means also did they mention like how they discover this function? Like, did they switch from sigmoid to this function or?
Yeah, actually, it's there in the later section. They did some ablation with the activation functions, but they only reported for the VIT part. shall discuss later in the slide, I guess.
Yeah.
Once is there anything more to discuss in
Yeah. Yeah, no, that's all from my side. I think now Ayush will be taking over.
Okay.
this? I will present now.
I think just a time check. We have almost 13 minutes left. So I think we'll be able to complete in time.
Okay, I'll try. So, so next we will start with the experiments and results section, and we will try to make sense of why these results actually came. So in the first set of experiment, what they did they experimented on supervised fine-tuning of vision models. So the first was a VIT and second was a conv-nect. And they found that in case of VIT, the increase in performance was more as compared to conv-nect. So an intuition that I could think behind is that in case of VIT, they are more dependent upon batch normalization because the inherent architecture is a transformer model. Whereas in conv-nect, much of the information is still with the spatial channels, so the batch normalization does not affect it much. So that could be the reason most of them have same results or very less increase.
Sorry, is it batch normalization or layer normalization we are
Oh,
talking
I'm
about?
Yeah, I
sorry.
guess you said it will be reverse.
Yes. And
Okay.
do you think anything more could be added to this?
Yeah, I mean,
Okay,
yeah, right.
so we'll go ahead. So next they did was to check on how the supervised fine-tuning work for vision models. So for this, they took two ways to do self-supervised fine-tuning. First is the MAE. So what MAE essentially does is mask some patches in the image and then ask the model to predict those patches. And in a way, the model would learn the representation of images. And in Dino is a kind of a student and teacher model relationship where there is a teacher model which is a bigger VIT and a smaller model which is a smaller VIT. And what essentially it does, for example, I have a single image and one is rotated and one is cropped. So a cropped image would be given to a teacher model and the rotated image would be given to a student model. But the images would be same. So what they would try to do is that the student model output would try to align itself to the teacher model output on that ablated set of images. So the model generalizes in case of any ablation or changes. So in this as well, the Dino VIT performed better as compared to MAE. And I tried thinking of some intuition, but I couldn't arrive at any. So can you think of something why this could be happening?
Which with MA, what's the MA model? Can you
So
expand
what
it for me?
what MAE model does is that there is an image, it would be divided into patches. Okay. So what essentially it does is that it makes model learn and I'm missing one thing. So it divides into patches and masks some of the patches. So suppose 50% of the image patches are marked and 50% are visible. So what this ME method would try to do is make model predict those patches. So in this
Masked
way,
image modeling. Okay.
it would try to learn the representation of image. And in Dino, it is a student and teacher model relationship. So in case of Dino, the performance increase was more. And why could that be?
I feel sometimes this delta is too small to also comment.
Yeah.
That's I was thinking. Maybe it's random.
Matlab, the drop in batch norm
Mm-hmm.
was significant. There we could draw a conclusion. Like there was 7% drop, I think, in
Mm-hmm.
batch norm for ResNet compared to a DYT.
Exactly.
But this one is too small to actually comment. Like this could be just on the samples that they have taken to fine tune.
Okay. That makes sense.
This is within the margin of error. Yes.
Yeah.
I think something is wrong with the presentation. Just wait a minute. Internet is not working, I think.
Internet seems to be working. Can you stop share and present again?
Now it's working. Is it visible now?
Uh, Not able to see a screen.
Sure. Mm, just a minute.
Ayush, if you want, I can present my screen.
Actually, that would be better.
Yeah, just give me 1 second.
Yes. Uh, can you move to the next slide, please? Huh. So next they did was the experiment with different sizes of diffusion transformers, and they tested in an ImageNet 1K dataset, and the changes were quite marginal, so we can't comment on that. And next they did the pre-training on different
What
variation.
is FID reported?
So FID. So let me elaborate more on that. So what FID is that it measures the how well a image is generated. So for example, there is a diffusion model and you pass the image through it. You pass the prompt and you got an image. है ना? So what FID does is that it there would be a ground truth image, for example, of an aeroplane, and they would pass it through an inception V3 model. So you have a ground truth image of aeroplane, you pass it through an inception V3 model, and you have a generated image, and you pass it through that inception V3 model. And then at a specific layer, as far as I remember, it was pool 3 layer. So they extract the feature maps of both of these images, and then they try to calculate a distance between these two distributions, how closely these two images are related. It is much
Hmm.
better than directly comparing the pixel values because it would only capture the exact pixel locations in the image, and using the middle layers of a model like Inception V3, which captures semantic information whether the two images are similar or not. So
Got it.
that's what they have reported here.
Got it.
Yeah. So next, in experiment 4, they did some ablation on the sizes of models, and consistently they found that the DYT performed either worse, very slightly worse though, and very similar to the RMS norm.
Hmm.
Can we move to next?
Yeah, yeah.
So these were again two different kinds of model which I didn't get to know much about it. So first is the wave to wave transformer model. So from the little which I studied about it, it is basically similar to BERT, where they would have a waveform of audio. They would first convert it to different sections, discretize the waveform, and then put a transformer layer on top of it and try to uh, predict the mask token which would be there to predict. So similar, it would learn the representation of an audio waveform, and then later it can be used to fine tune on a downstream task. And similarly is for this Hyena DNA model, where there would be DNA sequences and there would be attention, and it would try to predict the next DNA sequence in the. And in both of these, they found consistently performed close to each other. Layer
Got
number.
it.
So this is something interesting. So uh, as we all know that what RMS norm does is that uh, it does not have a mean, and it simply has a standard deviation with which it scales all the value. So the standard deviation is the key. So what would we want from an alpha? Would it play the role of a standard deviation? And this could be, and we can clearly see from both of these graphs that the one upon a standard deviation thing and alpha strongly correlate with each other, both in layer number 5, layer number 20, and both at the time of inference and also at the time of training. They correlate well with each other. So that was a strong indication that it works well.
Hmm.
Interesting.
So essentially, what it is saying is all that batch norm and layer norm was doing in most of the cases was standardization.
Yes.
It was less, or at least for the transformer networks. I think
Hmm.
these layers are from the transformer networks.
Haha.
So transformer-based models, they're saying there is less information sharing between two different examples or layers. Uh, all it was essentially doing was standardization. So then it is able to kind of, through that learnability, able to mimic the standard deviation of the data, etc.
And at the last, they show how it performs. It performs better than all the previous methods like layer norm and KIPNet, Sigma,
Mm.
reparameter. You can go to next one. This was clearly explained previously. So, what DYT does is that it reduces the computation that we have to do. That reduces the computation for the statistics that we have to do. So in RMS norm, we have to compute this only the standard deviation, but in DYT we don't have to compute anything. So what they experimented with is that they used 100 forward passes and 100 forward plus backward passes on a single token sequence, and found that the time were consistently less, which was quite evident with it. And next was the ablation on the uh, activation functions that I was talking previously. So they found that TANH performed better than hard TANH and sigmoid. For identity function, it was quite evident that it would perform better because identity was simply there was no normalization identity. But the interesting thing was that it performed very slightly better than sigmoid as well. That could be something we can talk about.
What is in the efficiency of DYT? What is that layer and model column?
Training
Uh,
of
Maybe for a
I
single
think
layer.
yeah, exactly. For a single layer and an entire model, I think it was.
Yeah, but a model has so many layers. How
Hmm.
is single layer 2 seconds and model 14 seconds?
Okay, let me check in just a minute. Maybe I missed it.
I think this is the overall latency for inference.
Sure, but what is layer? What is for model? It makes sense, okay. But what is this layer latency?
Just a minute. Hmm, 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 hmm.
I think time taken to compute activations of one single layer.
But that is too much. 2 seconds is too much.
Hmm, hmm. Yes, I found it. A single sequence consistently perform compared to RMS normal layers with a similar trend also generated time. I think it's for a single layer only, as far as they mention. DYT layer significantly reduce computation time compared to RMS norm layer. That's all they mention in the paper.
Okay. Cool, cool.
Maybe
It
it's true.
might be something different. Maybe it's summing the 100, the time for all the 100 passes, but for model, it is taking the average. I don't know.
Hmm.
But if it is taking one, like 2 seconds for one layer, that does not make sense. Like if,
Maybe doing for all the 100 passes and then taking the.
yep.
That could be.
For a
But
Llama 7B, I think how many layer norms will be there? It would be around 70 or 65,
right,
60, 70 layer norms. Ta? So if
270.
one layer is taking 2 seconds, it would take 120 seconds or 2 minutes. तो
That's
वो
true.
sense नहीं बन रहा है.
Hmm.
अभी तो layer norm के अलावा there's multiplication of attention and all that.
Hmm.
But anyways,
Against RMS norm by measuring the total time taken for 100 forward passes and 100 forward backward passes. Okay. Total time across 100 forward passes. So essentially the time is 2.1 divided by 100 seconds.
but model के लिए मतलब it's not correlating well. अगर layer 2.1 seconds है total 100 के लिए, model के लिए total 100 cannot be 14.1.
Makes sense. Not sure what's going on.
Maybe we're missing something here, but the point is clear. It's efficient. That is the benefit. Yeah, we can go to the next one. We're just out of time, so we can quickly complete.
So the next was the ablation with no the
Hmm.
conclusion in the next was the ablation with TANH and alpha. So with TANH, what they found that TANH performed consistently better than the hard TANH and sigmoid. Hard TANH and identity are pretty clear, but sigmoid and TANH could be talked about. Well, although the gap is
Even gap is similar. Like I think it's more about just the sigmoid.
just about
Yeah, hard tannage, for example, like hard tannage is very like that is fine, but sigmoid and tannage could be like in this case, hard tannage is performing better, like similar to tannage and better than sigmoid. But I think the main benefit is that squashing. Tannage gives more flexibility for squashing. That is all.
Yes, we can move to the conclusion now. So the conclusion that we can draw from entire of this that dynamic tannage could be a good approximation of the normalization of the RMS norm, where the standard deviation could be replaced by an alpha, and it challenges the conventional understanding and necessity of normalization layer in training of neural networks, basically. And yeah, basically it performs better than layer norm, but it fails in batch normalization. Maybe they didn't mention more in that experiment, so that's what it is. Anything more it left, Vansh, or it is?
No, that's all.
Cool. Thank you so much, Vansh and Ayush. Guys, anyone has any questions? We can quickly cover 1 minute.
Thanks, Ayush. Thanks, Vansh. This was really great.
Perfect. Thank you, folks. Lovely discussing this paper. We'll put out the video for this and the link to the Research Jam session 3 pretty soon. Let us know if there's any particular paper you want to get covered. Perfect. Thank you, folks.
Thank you.
Thank you.